Welcome to a new exciting episode of Scientific Thoughts. Deep within the constellation Taurus, some 6,500 light-years from Earth, lies the magnificent Crab Nebula. This stunning object is the principal item in the Messier catalogue of night sky objects that astronomers use today. First spotted in the mid-18th century, astronomers quickly linked this cloud of interstellar gas to a great supernova explosion that had illuminated the sky in the same spot around 700 years prior. Ever since, the Crab Nebula has stood out as a source of intrigue, becoming one of the most well-known and extensively studied objects in the sky, continually surprising astronomers as technology to probe it has improved. By the late 1960s, the advent of radio astronomy revealed that the Crab Nebula was hiding another object left over from the supernova, a rapidly rotating neutron star. Neutron stars represent the final form of matter before it turns into a black hole and have played an instrumental role in lacing our galaxy with the ingredients for life. Today, we will revisit these mind-bending objects, focusing on the incredible power of pulsars. Neutron stars do not arise from bodies like the Sun. When a star similar to the Sun nears the end of its life cycle, it swells up to a red giant and ultimately falls apart, exposing its core to form a compact white dwarf. However, for much larger, less stable stars at least 10 times the mass of our Sun, a different fate awaits. These massive stars eventually run out of fuel and collapse under their own tremendous weight, their outer layers compressing the iron core before bouncing back and exploding in a blinding supernova event. What happens next depends on the mass of the collapsing stellar core. If it weighs more than 3 times the mass of the Sun, nothing can hold back a runaway gravitational collapse, which continues to compress matter beyond its shore's chilled radius, forming an event horizon and ultimately a black hole. But if the core's mass is below this critical threshold, the collapse halts, forming a neutron star. As molecules are squashed together, temperatures climb so high that they break apart atomic structures, converting the core's iron mass into a dense soup of subatomic particles. Free-roaming, negatively charged electrons are crushed into exposed atomic nuclei, merging with positively charged protons to yield an abundance of neutral neutrons. The core, now a fraction of its original size, is jam-packed with excess neutrons, where degeneracy pressure from neutrons switching between quantum states resists further compression. This halts the collapse when the body is no more than about 25 kilometers wide, with its contents packed as tightly as an atomic nucleus. A neutron star's outer layers ricochet and explode in a supernova, leaving behind the neutron star itself. These stars contain the mass of up to 2 solar systems packed into a sphere no larger than a city like Boston, Frankfurt, or Cincinnati. This extreme compression drives some of the most intense physical phenomena observed in space. On the outside, a rigid shell of superheated iron encloses the neutron star, its gravitational influence so strong that the escape velocity is above half the speed of light. This gravity even stretches and dilates time, similar to the effect of a black hole. These iron shells sizzle at blistering temperatures for hundreds of millions of years, with the closest known neutron star to Earth radiating at almost 500,000 Kelvin. Yet even this temperature pales in comparison to the environment inside the neutron star. Beneath its crust lies a crystalline mantle of so-called nuclear pasta, long strings of neutron-degenerate material in intermediary states before becoming bulk neutronium, that rise to exist in a superfluid state at the core. The swirling of this superfluid, combined with the rotational velocity of the body, amplifies the neutron star's extraordinary magnetic field, making it hundreds of billions of times stronger than Earth's. Indeed, neutron stars are the most powerful magnets in the universe, exhibiting a broad range of electromagnetic phenomena as a result. They stand out among the billions of stars in our galaxy and even from other galaxies, although rarely in the visible spectrum of light. Instead, neutron stars are most prominent in radio, X-ray, or gamma-ray frequencies, with their spectra revealing much about the type of neutron star and its surroundings. As a neutron star rotates, particles within its magnetosphere are transported toward the polar caps along magnetic flux lines. When these particles arrive, they are repelled and blasted into space at relativistic velocities, emitting synchrotron radiation most prominently in radio wavelengths. Because these polar caps are not aligned with the neutron star's rotation, their movement swings beams of radio energy around the body like a lighthouse, sometimes sweeping in the direction of Earth. These signals often reach our planet as evenly spaced pulses, detectable as a series of periodic bursts. This is how we first detected neutron stars in the wild, through their pulsar beams of radio emission. The first real evidence came in 1967 when postgraduate Cambridge student Jocelyn Bell Burnell discovered a stream of galactic pulses occurring 1.3 seconds apart with pinpoint precision. Initially baffling scientists, who speculated about artificial communication from another intelligent species, a handful of similar radio sources soon favored a more natural origin, rapidly rotating neutron stars. Since then, over 3,200 neutron stars have been catalogued across the galactic disk, most of which are radio pulsars. Given the estimated number of supernovae over the Milky Way's 13 billion-year lifespan, there may be as many as 1 billion of these stellar cores within our galaxy and beyond. However, most are ancient, cooled, and slow to the point of being undetectable. Radio pulsars are usually at their hottest and spinning their fastest within the first million years of their inception from a supernova. If a pulsar exists in isolation, it loses rotational momentum over time, radiating gravitational and electromagnetic energy in a process known as spinning down. A pulsar's magnetic field lines drag on their surrounding space, decaying and transferring kinetic energy into electromagnetic radiation, responsible for the characteristic emissions from radio pulsars to more energetic X-ray and gamma-ray emitters. In a binary star system, if a pulsar hosts a stellar companion, it can gain energy from the donor object, usually a white dwarf or red giant. The companion's material is cast into space and swept into an accretion disk around the neutron star. Particles from this disk are fed onto the pulsar's surface, increasing its mass and rate of rotation in a process known as spinning up. These accretion-powered pulsars, or X-ray pulsars, are prominent in X-ray bands. Electrons from the accretion disk decelerate in the magnetosphere, emitting high-energy X-rays from hotspots around the pulsar's polar caps, producing a signal similar to a radio pulsar. However, unlike radio pulsars, which only spin down, X-ray pulsars can speed up, slow down, or maintain consistent rotation rates. This process can spin pulsars up to velocities of hundreds of revolutions per second, producing millisecond pulsars, the fastest type of neutron star. Millisecond pulsars, also known as recycled pulsars, are spun up by accretion to a substantial portion of the speed of light, producing incredibly regular and periodic signals. These signals are so frequent that even the gravitational tug of asteroids on a pulsar can be reflected in its measurements of Doppler shift. The first exoplanets ever discovered in 1992 were found around the millisecond pulsar B1257+12, remaining the smallest known extrasolar bodies with masses and diameters comparable to the Moon. The first millisecond pulsar, B1937+21, discovered in 1982, persists as the second fastest, at 641 revolutions per second. Around 200 recycled pulsars have been identified in 4 decades, with about 130 found within globular star clusters containing tens of thousands of stars. The high stellar density of these environments lends itself to binary systems filled with ancient stars, many of which have transitioned into pulsars. The fastest known millisecond pulsar, as of now, is PSRJ 1748-2446 AD in the globular cluster Terzan 5, spinning at a staggering 716 Hz, or 43,000 times per minute. However, the rate of a neutron star's rotation is not the primary factor determining its magnetic field strength. That depends more on its age and the type of progenitor star. For example, HD 5166, a recently discovered massive magnetic helium star, has a field strength more than 100,000 times that of Earth. When this star transitions into a pulsar, its supercharged magnetic field will be amplified, giving rise to the most powerful type of neutron star in the universe, a magnetar. Magnetars are the most magnetic objects in the universe, with magnetic field strengths in the order of at least 100 trillion Gauss. The story of these objects dates back to 1979, when scientists spotted a peculiar source of gamma radiation flashing in the Large Magellanic Cloud. These soft gamma rays faded away for 2 months, returning on March 5 with one of the brightest gamma-ray outbursts recorded at the time. Scientists termed these signals soft gamma-ray repeaters, which periodically flashed with low-energy gamma rays before fading again for months or years. By comparing their rotation rates and levels of spin-down, scientists deduced that these objects had field strengths in the quadrillions of Gauss. Astronomers also uncovered anomalous X-ray pulsars with a different mechanism driving their emissions. These signals were similar to soft gamma-ray repeaters, suggesting a shared origin. Both are products of explosions, eruptions, and quakes on magnetars. Magnetars are rare, with only about 25 known around the galaxy, representing a brief phase in the life cycle of highly magnetized neutron stars. During this phase, magnetic reconnect ion, megaflares, and field decay cause some of the most energetic electromagnetic activity observed. An active magnetar generates massive voltage differences between its poles, with electrons and positrons being accelerated along the magnetic field lines until their mutual annihilation. Protons interact with the field and magnetosphere, emitting gamma rays and X-rays before the magnetar decays within tens of thousands of years. These emissions can release more energy in fractions of a second than the Sun outputs in 100,000 years, propelling electrons, protons, and positrons away from the magnetar. This generates dazzling auroras and emissions that can eclipse other objects in space. The death of these magnetars is marked by the catastrophic release of stored energy through starquakes and gamma-ray bursts. These bursts occur from various types of stars, but those originating from magnetars are distinguished by their soft gamma-ray signals, similar to the brightest gamma-ray burst recorded on December 27, 2004. This gamma-ray burst, arriving at Earth from SGR 1806-20, is still the brightest and most energetic known explosion outside the Solar System. Its initial flare was so intense that it temporarily affected the upper atmosphere's ionisation. The source of the burst is a known magnetar, located in a nearby galaxy cluster approximately 50,000 light-years away. This burst alone released more energy than the Sun will in its entire 10 billion-year lifespan. These gamma-ray events have been instrumental in advancing our understanding of the universe, and some astronomers speculate that many gamma-ray bursts detected from distant galaxies might originate from rapidly decaying magnetars. They may also have played a significant role in Earth's history, potentially contributing to mass extinction events. Regardless of their potential past impact, magnetars remain the most fascinating and potent neutron stars ever discovered. Neutron stars, whether pulsars, Millisecond pulsars, or magnetars, have taught us much about our galaxy and the universe. They serve as natural laboratories for testing theories of matter, electromagnetism, and gravity under the most extreme conditions. Their immense gravitational pull and rapid rotation provide insight into the behavior of matter and the fabric of space-time. As we continue to study these remnants of stellar evolution, they will undoubtedly unveil more secrets about the cosmos. If such an outburst occurred within even 10 light-years of our planet, it would spell the end of most life on Earth. The intense gamma radiation would completely degrade our planet's protective magnetic bubble, allowing pervasive solar radiation to erode the atmosphere's protective layers, boil away our oceans, and render the surface of this planet a parched, airless wasteland subjected to untenable levels of radiation. And gamma rays aren't the only type of abundant radiation thought to stream from the crevasses of starquakes. They have also been suggested as a potential source of fast radio bursts, anomalous, short-lived signals brimming with radio noise, for which no concrete theory exists to explain some 700 recorded to date. Moreover, around 30 of these radio bursts are repeaters, not regular sources of emission, but recurring nonetheless. Therefore, they may share a similar origin to the soft gamma-ray repeater emissions arising from the quaking shells of magnetars. Alternatively, they may be produced when neutron stars collide, crashing into and consuming one another, facilitating yet more colossal stellar explosions. As mentioned earlier, the fastest spinning pulsars are very precise indicators of their surrounding environment. American physicists Joseph Taylor and Russell Hulse used this method to capture observational evidence of general relativity at work around the first-ever binary pulsar, winning a Nobel Prize in 1993. Their Doppler shift measurement showed a rapidly spinning pulsar, 1913+16, and a slower, cooler neutron star companion sinking towards each other, their orbits tightening as energy was lost from the system, radiated away as ripples in the fabric of spacetime, a key prediction of Einstein some 80 years prior. This was the first time that gravitational waves had been observed empirically, but another 30 years would pass before humanity pinned down their first direct detection in 2015 with the Laser Interferometer Gravitational Wave Observatory. When two massive, inwardly spiraling compact bodies draw very close to one another, whether they're black holes, neutron stars, or both, their gargantuan masses and influences are accelerated to velocities eventually reaching 2/3 the speed of light. The rapid orbital movement of such pervasive gravitational influences raises the spacetime around the merger, sending gravity ripples pinging off omnidirectionally for billions of light-years across space, ultimately detected by LIGO's sensitive array of wave-seeking instruments. The detection of these signals often serves as a precursor for pinpointing the precise location of the cataclysmic event that soon follows. Once a pair of merging neutron stars are sufficiently close, they are accelerated to speeds exceeding their own escape velocities, rupturing their iron shells and briefly exposing their inner contents to the near vacuum of space. A small fraction of the superdense material escapes, suddenly under a fraction of the pressure it was within its progenitor neutron star, causing it to ignite and explode in a tremendous kilonova, as powerful as the strongest supernovae. Like supernovae, the ejecta of these explosions are laced with heavy atomic nuclei, intersected by free neutrons and protons, which combine through the R and P processes to yield troves of the heaviest elements in the universe, from iron, gold, and silver to platinum, uranium, and thorium, along with everything in between. It is now generally believed that kilonovae, not supernovae, are responsible for seeding the galactic medium with most of its heavy, complex elements, including many of the ingredients for life on this world. Like exploding stars, colliding neutron stars also produce their own class of gamma-ray bursts, huge explosions of the shortest wavelength radiation, which are seen lighting up the skies of gamma-ray telescopes every other day or so. Longer gamma-ray bursts, lasting from a few seconds to a couple of minutes, are thought to result from supernovae. During a kilonova, the exposure of the shattered neutron star's interiors to space is much briefer, leaving only enough time for a short gamma-ray burst and perhaps a fast radio burst, lasting 2 seconds or less. Almost immediately, however, the debris from both bygone neutron stars is pulled back in to form a new composite object, which itself undergoes a gravitational collapse under the same conditions as before. If the combined mass is above 2.5 to 3 times the mass of our Sun, the bodies will form a new black hole. Below this threshold, they will reconvene into a new, heavier recycled pulsar, or perhaps a magnetar, restarting its evolutionary cycle. The question is, what if the combined mass comes in right between these two eventualities, where the compression is substantial enough to overcome the force exerted by neutrons, but not quite significant enough to compress beyond the radius needed for an event horizon? You would wind up with a boundary object, a collapsed star so dense that even neutrons come unbound into their smaller subsets, under conditions so extreme they resemble those of the early universe. Neutrons, the two particles comprising the nucleus of an atom, are both types of hadrons, a class of subatomic particle composed of 2 or more quarks. Quarks are a type of elementary particle in that they have no further subsets that pressure or heat can split them into. They are the tiniest pixels of mass in nature and were the first kind of matter to form in the young universe. We don't see free quarks in the wild today, however, as creating quark matter analogous to neutronium requires unfathomable temperatures and densities, even greater than those found in a neutron star. The last time such conditions existed was just after the universe's inception, when its entire contents were crammed into a comparatively minuscule area, packed even tighter than the nucleus of an atom. An ocean of primordial quark-gluon plasma permeated all of space, oozing with the essence of the strong nuclear force. But over time, space expanded, and this ocean spread out, cooling and condensing into hadrons, followed by other, larger aggregations. Ever since, free quarks have not been seen in nature. But if a newly formed, accreting neutron star treads the fine line of the Tolman-Oppenheimer-Volkov limit for a black hole, a certain borderline mass may induce the kind of gravitational collapse that can overcome neutron pressure to achieve quark deconfinement. Neutronium would be broken down into an even more compressed and energetic quark-gluon superfluid, held apart by its own, even stronger nuclear repulsion against gravity, giving the dead star the density of a large hadron as opposed to a large atomic nucleus. Such an object is known as the hypothetical quark star. Quark stars are to quarks what neutron stars are to neutrons, smaller, even more compressed spheres of quark-gluon matter, likely appearing similar to a neutron star but with their unique set of emissions. If a quark star is two-flavor, consisting entirely of fundamental, first-generation up and down quarks, it may appear very similar to a neutron star indeed, consisting only of a quark-gluon core concealed by layers of less pressurized nuclear matter, with a maximum diameter of about 15 kilometers. On the other hand, a quark star could be three-flavor, containing an almost equally balanced number of up and down quarks alongside heavier, second-generation strange quarks. Strange quarks are one of 6 types in total. They have the same charge as down quarks, but can be converted into up quarks via nuclear forces. Thus, their presence would drastically alter the recipe for a quark star by making it significantly more stable in low-energy states. In fact, strange quark matter may be the one true ground state for mass at the highest densities and has been described with many different mathematical frameworks as both perfectly stable and everlasting. As such, a three-flavor strange quark star with strange matter in its interior is inherently self-bound and may not even need a solid nuclear surface to bind it together. It may instead have a transient surface, playing out a volatile cycle of emissions potentially detectable from Earth. Initially, a strange star would have no solid surface, defined by a boundary where quark density abruptly reduces to zero. Over time, blistering electrical currents from further down would force any surviving scraps of normal, nuclear matter outwards, collecting just beyond the edge of the quark matter into a tangible, decoupled, scarcely stable crust. This surface would be extremely short-lived, soon collapsing back into the strange star to catalyze a plethora of gamma-ray emissions, possibly explaining anomalous soft gamma-ray repeaters, which show departures from conventional magnetars. Thereafter, the bare, chaotic strange quark interior would once again be exposed to the cold expanse of outer space. Because strange matter is thought to be so stable, any lost from the body during this cycle of outbursts would likely maintain its ground state, manifesting as a particle-sized nugget of strange quark matter known as a strangelet. If such a stray, free-streaming nugget entered a system with more conventional celestial objects, like ordinary stars and planets, it might contaminate an impactor and pass on its ground state properties, dissolving the structures of atoms and reducing them to strange quark matter. This would induce a snowballing process causing the bodies collapse into a strange quark planet or strange quark dwarf, though the long-term stability of these middle-range mass strange objects is still debated. With no means to distinguish them from conventional pulsars, theories on quark and strange stars remain speculative. They have been predicted and described mathematically but never reflected in reality by observations. One more type of so-called hybrid neutron star might be possible and may have occurred within our cosmic backyard. Do like and subscribe to our channel for more interesting videos. Have a good day.